and gentlemen, professors and colleagues. Today I would like to give you the brief idea of what are Bragg's and one-layer experiments, as well as some cases of X-ray diffraction. This thing is so wide and includes so many topics that it's quite impossible to fit them into one presentation in half an hour. However, I will try to do my best. Besides, I'm not a specialist in this field, but we will see. General presentation is divided into two parts. The first one is dedicated to X-ray diffraction and Bragg's law. The next one to low-layer equation. All of them are divided into three subtopics. First of them is the brief history, main principles and background, and the implication. So let's proceed to a quick history of X-ray. I'm quite sure that on that cold November day, 1895, when William Röntgen discovered his X-rays, he wasn't even thinking that this will put the beginning to a whole new sphere, a whole new area of investigation that will evolve even 2 centuries after the development. As all the things in physics, almost all the things in physics, this was done by an accident. He was actually doing some experiments with the evacuated glass tubes when noticed that the screen started to glow after the rays hit it. He was amused by this fact, as the screen was situated too far from the source of X-rays. He was even more amused when he noticed that if to put a hand between the source and the screen, you will get a precise, really nice picture of your bones. Actually, this is not his hand. The first picture of human flesh taken by the X-rays was done on his wife. I don't know whether she was boring him or whether she was not letting him to do his experiments, but he decided to do the first experiment on her. Actually, this is one of those kind of experiments that find its application just a year after the development. And in 1896, it was already applied in medicine for determining the structure of bones. First, people were kind of induced and even scared after seeing their bones, as it was connected with death and illness. A lot of people even fainted after seeing the picture. The development of the X-rays, the investigation of X-rays, put a whole new beginning for different experiments. And a lot of physicians try to do their best in this field, as it seems very prospective for them. Among them are, of course, father and son team, Sir William Henry Bragg and Sir William Lawrence Bragg. They are the only father-son team at that time, and as I'm not mistaken so far, who had won Nobel Prize at the same time for their total contribution to the investigation of crystalline solids using X-rays. Other pairs like J.J. Thomson and George Thomson, or father and son Kernberg, they have won a Nobel Prize, but for different contributions. And besides, William Lawrence Bragg was only 25 years when he won. So we have, like, most of us still have time. It was his father, William Henry Bragg, who was mostly doing the experiments. A year after the discovery of X-rays, he was so fascinated by the fact. So he had the idea to find out, is it possible to reveal the structure of crystal while using X-rays? Actually, he was a proponent of a party that considered X-rays to be particles. On the contrary, von Laurier seemed to be advocating the Theta theory. But by using and by doing his experiments, William Henry Bragg partly was sure that his point of view was right. But as we all know that it both waves and particles, but at that time there were a lot of arguing on this scene. At that time, William Lawrence Bragg wanted to become the director of the Cavendish Laboratory in Cambridge, England. And it was precisely in this laboratory where in the 1950s, Professor Watson and Professor Crick, using X-ray diffraction technique, has revealed the structure of DNA. And this is the picture taken just at that time. It would be fancy if I would read the full name of DNA, but I'm sure I'm not succeeding in this. when Professor James Chadwick proved the existence of the neutrons by the X-ray diffraction technique. However, during the speech of Professor Wu at the Nobel lecture in 1936, it was said that probably Newton diffraction will never be such a good field to study. It will be never a useful tool because of our low source intensity. As we all know, today is totally different. Even great physics could make some mistakes. A little physical background before proceeding to the Bragg's law, scattering. I think we shouldn't be scientists to know what is scattering. Like playing billiard, we all know when we hit the white ball, first it goes through the straight trajectory. But then, after hitting other balls, it's deviate from it. So we will have, so it's hitting the scattering center of the propagation medium and go to another trajectory. This is exactly the idea that lies behind the scattering in physical meaning. As we're talking about physics of particles, this depending on the scattering centers, we can have neutrons scattered by the atom nucleus. We have X-rays, interaction with the electron density, and the electron scattered by electric or magnetic fields. As we're talking about scattering, one must say about elastic and inelastic scattering. And depending on, we all know that there is a role of energy preservation, but depending on whether there is energy loss, like in the case of inelastic scattering, or there is no energy loss, so E prime, the energy after the heating is the same as the energy before the heating.
Well, there is never energy loss, simply it's transferred to
to the medium, yes, but generally. So, in elastic, we have several types depending on the wavelengths and the size of the object of the scatter. We have Rayleigh, Mie, geometric, and Thompson. While in elastic are Compton, Brilliant, and Drummond. I must say that generally we have inelastic scattering because, of course, the medium is not ideal and there are fluctuations, vibrations, we have phonons, and so on. However, there are some differences, and the idea is the same for all of these types. However, for example, in Compton scattering, we have random incoherent thermal fluctuations, while in Brilliant scattering, they are correlated and periodic. Then proceeding to diffraction. Generally, diffraction is a bending of the waves around small objects or passing through the slit or spreading out of the waves past small apertures. Let's, for example, have two simple waves, P1 and P2. The difference between them is only the phase. We all know that as a result, we can have an enhanced wave if the phase is the same, or the phase will go to the zero. So we will have interference pattern, which was shown, for example, by the experiment of Thomas Young, double slit. It also is a result of the different paths of the waves, which lead to the phase shift, and which show us the different interference patterns, so minimus and maximus on the slit. So generally, talking about crystal diffraction, we have the same phenomena, but we can talk about real space description as it was done by Bragg. Also momentum or case-space description, which is more preferable in the case of crystallography. Diffraction in a sense of quantum physics is very important because now we can consider neutrons and electrons to be the scattering centers. Interesting that the actual word diffraction was coined in 1616 by Italian physician Francesco Maria Grimaldi, and he was the first one to record accurate observation. When talking about the quantum mechanics, diffraction, the wavelength associated with the particle is the de Broglie valence, and it is presented by the formula where valence is equal to Planck's constants divided by the momentum, which is mass times velocity. So, the mathematical form of Bragg's law. Sooner or later, all the physicians will come to the definition of Bragg's law, as we are all using, most of us are using X-ray diffraction to determine the structure of crystal or its quality. So it is like one of these formulas that everybody should learn by heart. N lambda is equal to 2 sinus theta, where n is some positive integer, lambda is of course the wavelength of incident wave, d is the spacing between the planes, and theta is the angle between the incident ray and the scattering planes. The general idea of the phenomenon is presented on this picture, where we have two incident beams 1 and 2, which are scattered by the atoms and produce scattering beams 1' and 2'. Scattered, the distance between the planes is d, and the angle of diffraction is theta. We will get a really good diffraction pattern by measuring the intensity of scattered waves as the function of scattered angle. Strong intensities, also known as Bragg peaks, are obtained only in a case when the scattered angle satisfies the Bragg's rule, but it also is the ideal situation. The physical explanation is easy, as we have electromagnetic radiation or subatomic particle waves with the wavelengths comparable to atomic spacing, so we can see the phenomenon of diffraction. They are incident upon some crystalline sample scattered from the atoms in the system, and they undergo a constructive interference in order to have a constructive interference in order to see something. So we have this Bragg's law. The mathematical derivation is not also so hard. As already mentioned, we have beams 1 and 2. Let us assume that they are parallel and they are in phase. Then the difference between beams 1 and 2 will be AC. We'll use this part AC, and between diffracted beams 1' and 2' will be BC, which are parts of the triangular AC, for example, O and BCO. As we're seeing, we have two triangulars, and from a simple geometry, we may count that AC is equal to BC and equal to sinus theta. From other point of view, the sum of these differences between the beams, between the lengths of the waves, AC plus BC, should be equal to the n lambda. So we will have the precisely same phase shift. And we have, from one point of view, n lambda is equal to AC plus BC. From other, it's equal to sinus theta. Combining these two equations, we will get the Bragg's law. Depending on the theta angle, we can have different diffraction orders. Generally, we are taking into the account mostly first diffraction order, as it's given more importance because we have high intensity, thus it's corresponding to the high harmonics. So the lower the angle, the better picture we have. But to get the full picture of the crystalline structure of our investigated sample, it's better to do different angle measurements. And I will show you later on the equipment how it is done. Now it's good time to proceed to the Miller indices. Generally, the orientation of the crystal plane may be defined by considering how the plane, or actually the tableau of planes, are intersecting the reciprocal lattice vectors. So for this we have Miller indices, just the integers h, k, and l, notation in the system in crystallography for the planes in the crystal or Bragg lattices. For example, let us have a cubic primitive cell with the vectors a1, a2, and a3. In this case, we have the Miller indices 1, 0, 0, notating as a plane which is orthogonal to the direction h. We have the yellow one plane, the 0, 1, 0, which is orthogonal to a direction k, and the green one, 0, 0, 1, perpendicular to n. It's better to show the video to represent how the planes are indexing. It's really easy. So having some primitive cubic lattice and a primitive cubic cell within some system XYZ, coordinate system XYZ, we may have perimeters A, which lays on x-axis, perimeter B on y-axis, and perimeter C on z-axis. Let us assume that we have some plane that intersects x and that in the middle and plane. In the case when we don't have any interceptions, we will just get 0, as the theoretical interception of a real plane is somewhere there in the infinity, and by dividing we will have 0 in the Miller indices. And sometimes we get the line above, which means that we're just changing the corner of our coordinate system, and we will get minus in our Miller indices, like, for example, in here. So once more, reciprocal lattice vectors is represented by k, which is equal to hb1 plus kb2 plus lb3, where h, k, and l are the Miller indices. b1, b2, b3 are the reciprocal lattice vectors. The connection between the real and the reciprocal one is presented by the formula above. Actually, it is the lattice spacing and the reciprocal vectors, which is equal to alpha divided by the square root of sum of squares of Miller indices, where alpha is the lattice spacing. Combining these relations, we can have the actual relation with Bragg's law. However, it is different depending on the primitive sum. This and the primitive vectors for every kind of primitive sum is different. For example, the previous one was for cubic, and these are for tetragonal, orthorhombic, hexagonal, and monophobic. And they're also called key spacing. One more example for selection rules of the Miller indices for some of the Bravo lattice, at least for primitive cubic. So we see that we can really, depending on the compounds, count the allowed reflection and the forbidden one. And it is very easy to count knowing at least h, k, and l. That's why those h, k, and l Miller indices are so important.
If I may for a second, assume I see, which is, I think it's a very nice example. Polonium is the only element in periodic table of all crystalline materials which crystallize in simple cubic form. And it is understood why only for the last couple of years. It is a consequence of relativistic interactions because it's a very heavy element. And that's why these relativistic corrections make the lowest energy of the crystal just a simple cubic. It's the only element which crystallizes in that form.
Have all the reflections are low, there is no forbidden, it's very easy to take into account this compound, indeed. So, proceeding to practice, we're in the middle, sorry, it was such a long presentation. X-ray diffraction is a very useful tool, and it was used not only in electron diffraction for determining the crystal structure and its quality, but also in mineralogy and metallurgy. For example, it was in 1924 it was first used to determine the structure of garnet. And here you may see a very interesting picture. And 2012, when the Curiosity rover landed on Mars planet, he took the example of the Martian soil, and after analyzing, he produced this picture. So this is a picture of the Martian soil, which seems very similar to what we have on Earth on Hawaiian volcanoes. Of course, the electron diffraction, as already mentioned. Usually, electron diffraction is good for, it produces very good sharp intensity peaks for metals and very weak for biological compounds. However, it was used in biology and gave really great results. As here you can see there is a 3D structure solved by Dorothy Crawford Hodgkin in 1945 of penicillin. This lady, this doctor, she was using, as she just not solved the structure of penicillin, but also the cholesterol, penicillin, vitamin B12, which is very complicated, for which she has won a Nobel Prize. Also, she dedicated 30 years using the X-ray diffraction technique to solve the structure of the insulin, and she succeeded. And the neutron diffraction. Or, I don't know, to do some interesting artistic things, probably also part of this, but here we see the nice picture taken using the X-ray diffraction of snowflakes, which reveals that the hexagonal symmetry is because of the tetrahedral arrangement of the hydrogen atoms around the water molecule, which is similar actually to silicon in silicon O2. diffraction has different techniques: single crystal, powder, thin films, and small angle diffraction. First three are dependent on the form of the sample we're investigating, and the last one give us the investigation in the angles between 0.1 to 10 degrees. By investigating with X-ray diffraction, we can get all kind of information. We can know the crystal structure, determinations, thin film quality, stress, strain, defects, size, and so on. And all this information is provided by the angular position, broadening of reflection, intensity of pace, and to the imaging. Actually, all of this we can see on the diffraction pattern, which I will show you later. As I already mentioned, neutron diffraction is very interesting. Just one slide of neutron diffraction. It's very interesting branch of the X-ray diffraction because it has a lot of advantages in comparison with electron diffraction. With electron diffraction, we're scattering on electrons. That's why the high intensities are for atoms with higher atomic order, with higher Z. That's why it has a dependence on the angle. However, here we doesn't have such a dependence, so we can do the pictures up to very high angles, nice pictures up to very nice angles. Also, we are scattering directly from the atom nucleus. That's why we can distinguish different isotopes. The only one disadvantage of this method is it's very, very expensive.
Well, it has another one. If you shine neutrons on heavy elements, they become radioactive after a while.
Yes. But it is very expensive. Actually, it's thousands, hundreds of dollars to set measurements. So, first equipment that has a structure similar to water and was built by William Henry Bragg and presented on this picture. The idea that lies behind it is very easy. We have some source of X-rays, for example, X-ray tube, and we have a crystal. Between them, we have some lead sheets to produce a different wavelengths. So they will give us good water-like propagation of the waves. And diffracting from the crystal, they are hitting the photographic plate and produce a diffraction pattern. For example, as it is shown on the picture from the left-hand side. Why it's such a powerful and such a great tool for determining the structure of the crystal? First, and the most important, it's non-destructive. It is the greatest advantages. Also, it is very sensitive. And for example, by using high-resolution X-ray diffraction, we can measure so thin films that they are like several nanometers thickness. More modern structure is presented in here. For example, we have the same X-ray tube. Instead, we have collimators and filters, and of course, to have the better intensive picture of diffraction pattern, we are using the detector in the end. The schematic presentation is on the right-hand side above. So, peak intensities depends on several things. Of course, the form factors and structure factor, scattering angle, and preferred orientation. So we can change those by rotating usually the crystal. There are several methods. This is one of them, by rotating crystal while using the same wavelengths. So we are changing omega and theta, kappa and phi. Also, it is dependent on some environmental factors like temperature and absorption. Dating diffraction theory that lies behind it. That we know that the main goal of X-ray diffraction is to determine the density of electrons, which is function f from r through the crystal, where r represents a 3D dimensional position vector within the crystal. To do this, we are collecting data, scattered data, and using the Fourier transformation reproduced by the formulas f from r and f from q, where we're having the integral for all the values of q, where q is also a 3D vector, which represents the point in reciprocal space. And we're actually moving in the direction of this q vector. However, we will got the information, only half of the information needed. We'll get only the magnitude part of the Fourier transformation. To get the phase, one need to obtain full sets of reflection with known alteration of scattering. In ideal case, f from q is equal to 0. And we will get the Bragg peaks only in the case when the Bragg conditions are right. However, we are dealing with, nothing is easy in our lives, so we're dealing with a real world, and there are some vibration around atoms, around the new positions, causing disorder, defects. That's why Bragg peaks have finite widths. In our institute, we have a possibility to measure using X-ray diffraction. To say the truth, I have never been in this part of the institute. I have never I'm amused by the information that is given on our website, and maybe one day we'll try to do the measurements of my samples with X-ray spectrometers. So the parameters are provided below. And we have the possibility to measure X-ray powder diffraction, so lattice quantums, phase analysis, structure, determination, reflectivity, roughness, and, which is more important, high-resolution X-ray diffraction. For example, let us assume we have a diffraction pattern taken from X-ray, high-resolution X-ray diffraction measurements. It accounts for 004 Bragg reflection. Taken from 100 nanometer samples, it's a gallium arsenide down below, presented by green line, it's as chrome, and the pink one annealed, as well as gallium bismuth arsenide doped with actually 0.3% of bismuth, and also annealed and as chrome. What we may say about the investigated samples looking at this picture? In the middle, we have a very good high peak, which is from the substrate, gallium arsenide. On the right, on the left-hand side, we have wider and lower peak, which is actually from our layers of gallium bismuth arsenide and the gallium arsenide. So, because they are looking at the fact that they are lower and wider, we may say, and the angle between the substrate peak and the film peak is quite wide. We may say the lattice parameters with the addition of bismuth, they increased, as well as increased the compressive strain, which is also presented in the table below. Annealing treatment, as we may see, presented by the red and the pink one curve, enhanced a little bit the process, however, not so dramatically. And if you look on the right-hand side, we will see interference fringes, which are actually very good visible. And by analyzing them, we may say about the quality of our films, which are very good, and to check the thickness of the samples. So, having a peak position, we may define geometrical parameters. Peak intensities go to electron density and influence by orientation. Peak shape tells us about the quality, crystalline size, strain, and influence from some setup. And angular position tells about lattice parameters, thickness, phase analysis. Just a quick overview for experiments that were done by Max Theodor Felix von Laurier. This is one more German physician who's also doing experiments in the field of X-ray diffraction with a crystal, and he actually won the Nobel Prize for discovery of the diffraction of X-rays by the crystal in 1940. He was inspired to do such investigations by his friend Paul Evaldo by using the wavelengths, by using small wavelengths with the crystals. Actually, he was, as I already told, he was a proponent of the wave party of X-rays. So he was always arguing with Bragg about the nature of X-rays. But he was forced to suggest that the incident X-rays must have only certain wavelengths to account for missing diffractive beams from the crystal. Some physical background, as for example plane wave, as a wave whose surface of constant phases are infinite, parallel planes of equal spacing, normal to direction of propagation, described by this formula. Once more about reciprocal lattice vector of Brevis lattice as a set of all vectors K for all real position R, described by these formulas, where reciprocal lattice is defined in terms of a Bragg lattice, is itself one of these 14 Bragg lattices, and reciprocal of the reciprocal lattice is the original direct one, like minus give to plus. One more reminder involves a connection between the real lattice and reciprocal lattice. So for example, we have the original real lattice, real coordinate system. Going to reciprocal, we will get the blue one. And A with a star is representing the parameters from reciprocal lattice, and they are only parallel to A. For example, A star is parallel to A only if A, B, and C are mutually orthogonal. Derivation of one-layer condition is actually very similar to derivation of Bragg's law. As Levchenko said, constructive interference occurs when the scattering vector is a reciprocal lattice vector. So we have precisely the same. We have two beams, K and K, that are parallel to each other, and scattering centers from agents, they have K prime scattering beams, scattered under the angle of theta, with this. We are forming two triangles with a hypotenuse at D, and the difference between the passes of the base is, of course, tan cosinus theta from these triangulars. The difference is presented. The path difference is D times the difference between cosinus theta. So, for example, unitary vector n prime. Condition for constructive interference for these beams to be in phase is presented in here, so it should be equivalent to n lambda. To do some simple mathematical derivation, we will have equation very close, very similar to the one I have mentioned already. And multiplying by e and raising to power of e, we will get e to the power of I. The difference between k, the vectors, times r is equal to 1. From this, we may say that diffraction occurs, that Levchenko was right, that diffraction occurs when the change in the base vectors, k prime minus k, is a vector of the reciprocal space, which is better visible on this picture, for example. So, difference between them is not such much. So, we're telling, when we're talking about Bragg reflection, we must notice that diffraction occurs when path length difference is equal to n lambda. And here, diffraction with scattering vector is equal to reciprocal 1. Equivalence to Bragg is written in here. Also, the connection between them is very easy, but to make our life better, the easiest derivation, the connection between Levchenko and Bragg equation is presented here in box. So we know that reciprocal vector is k and is equal to j, presented by h day1 plus chi b2 plus n b3. And knowing the equations, that k is equal to 2 decimus theta divided by lambda, and j is equal to 1 divided by d, the spacing between the planes. And as they are equal to each other, we may have the consequent result, which is actually the Bragg's equation. Diffraction occurs only when a reciprocal lattice points lies at the surface of the evil sphere. So, once more, we have a triangular of incident and diffracting beam HKL, our Miller indices plane. We have a reflecting sphere. That's how the L sphere is built, actually. And we have the limiting sphere. So, in order to record diffraction patterns, one must use a polychromatic radiation, so vary the sphere size to get the pattern. It's Levchenko method, or rotate the crystal, it's a Bragg method. Or use a powder sample, which will give us all angles diffractions. So that is how the Levchenko conducted his experiments. So we have a crystal, the idea is pretty much the same. So we have the crystal, we have the slit, an X-ray source of X-rays, X-ray tube. Only we are using white radiation in single fixed crystal. Only the points in hatchet region on the evil sphere are imaged on the slit. So all possible wavelengths choice of variable size, diffract, and finite camera angle. Also, he had two kinds of methods of measuring. He was using a straight transmission method when they first have source, sample, then, for example, some picture, and we will get the ellipse in the result. And the back reflection method when the film is placed between the X-ray source and the crystal. Here we got some hyperbola in the result. I think that's all, and thank you for your attention and your patience.
Thank you very